All right, we start chapter 5 now at this point here, and we are going into the trigonometry section. We will spend chapter 5, chapter 6, and if we get to chapter 7 in this chapter on trigonometry here. 5.1 has to deal with, we're not even going to get to trigonometry in 5.1. This is just a vocabulary, the whole concept of angle. We're going to bring in a lot of things from geometry back into here. So if you remember a lot of things from geometry, you're doing good. So this would be more like a little review from geometry sort of thing. This one, and the complements, supplements, you probably should know that from geometry. And then maybe, or maybe not, you might not know, find the arc length of a circle, find the area of the sector, and then one last one has to do with motion. But can we look at the linear and angular speed? Angular speed just means turning speed, that's turning. All right, so some vocabulary here. I think you guys know what array is. Array is a portion of a line that starts at a point and then goes on forever on one end. So one of those is called an endpoint. An angle really is formed if you take two rays and join them at a certain point right there. So really there's two little sides to this. There's an initial side right there where you start from, and then there's a terminal side of where you're actually going to end your angle. All right, and of course the vertex. The vertex is that little point right over here where they both connect. All right, as we said before here, here's your initial side, the terminal side of where it ends, and if we go counterclockwise, if we go against the clock, what we have ourselves is we have ourselves a positive angle. If our initial side is here, and then we go with the clock, or clockwise, what we have is we actually have a negative angle. And this little, it's a Greek letter, this is called theta. In mathematics, whenever you're thinking about just a single angle, then we're going to usually use theta for a single angle. Now if you have multiple angles, then we have to distinguish. We can't just put theta and theta. It's almost like putting x and x. That's not going to work. And so what we do is we use the first letter of the Greek alphabet called alpha, and another one called beta. Beta is almost like a little b with an extra little hook at the end. All right, what does this say? This says that you can have something called coterminal angles. You can start the initial side and go counterclockwise and finish over here. You can go clockwise. Notice that right over here there's one rotation. You could take not even a full rotation. You can go from here, you can stop here. That would be a coterminal angle with alpha. Or you can go swing all the way around. You can cause another coterminal angle here. So I guess the question is, how many coterminal angles can you have? That's the trivia question here. And you can have an infinite amount of coterminal angles. Because I can just go like this, that's once, right? They can do one revolution all the way around, that's two coterminal angles. You can go twice around, this can be three coterminal angles, so you can do this on forever. All right, and now we go on to something called a standard position. Standard position of an angle is when the vertex itself is right on the x and y coordinate system. And this was sort of the genius of how trigonometry started. In geometry, you know, you see sort of those angles are sort of out in space. Trigonometry started by placing this little vertex right over here, and by doing that we got ourselves a whole new branch of mathematics that was actually born. Okay, a few things here. Just the books just sort of quickly talks about here is this whole concept of quadrants here. No, just remember from geometry, maybe even algebra here. Remember, don't forget the quadrant system. We're going to really learn that in or use that in trigonometry here. So the quadrant number 1 is over here. Quadrant number 2 is on the upper left-hand corner. Quadrant number 3, lower left-hand corner. And quadrant number 4 is in the lower right-hand corner. So in this case, what we say is this angle, it is first of all, it's a standard position because of the vertex, which is this one right here. It's a negative angle because it goes clockwise, it goes this rotation. And it's in quadrant number 2. So there's a lot of information just about that angle right there. All right, we're going to talk about these a lot as well here. These are called quadrantal angles. And what are quadrantal angles is the terminal side ends right on one of the axes. And so if it ended on the positive y-axis, if it ended on the negative x-axis, the negative y-axis, or even a full rotation and ends on the positive x-axis, that would also be a quadrantal angle, or even 0 degrees. What happens, this is the initial side, doesn't go anywhere. The initial side is right on top of the terminal side. It was 0 degree change, and that's still considered an angle. All right, and just another one here, just for practice here. So notice this is going to be a positive angle. Notice you got one full rotation right here, and then you have an extra piece as well. So we say this is in standard position. It is a positive angle, and it goes and stops in quadrant 3, bottom left-hand corner. All right, types of angles. What types of angles do we have? Again, this is just still from geometry here. I think you guys know these quite a bit here. An acute angle. Acute angle is an angle that measures less than 90 degrees, or between 0 and 90 degrees, I should say. Right angle is one that's exactly 90 degrees. We have a fun little thing right here. We put a little box there to say that's exactly 90 degrees, and of course still the rotation here to show which way it went. An obtuse angle, it is an angle that measures more than 90 but less than 180. So it's somewhere here. If you think back to the previous slides, those should all end up in quadrant 2. Then we have the straight angle. Straight angle is one that measures exactly 180 degrees. So the terminal side finishes off on the negative x-axis. So practice problem for you. Can you draw for me an angle that is 225 degrees in standard position? All right, I'm going to give you a little bit of time here to do it. All right, let's go for it here. So first is we have to set up a y or x and y grid system. Once we set that up, don't forget this is about 90 degrees here. This is about 180 here. It is exactly 180. So 270 is down here if you sort of want to break things up into its little pieces here. So 225 degrees would be about right there. It's in quadrant 3. We have to show the rotation. It's positive, so we go from the x-axis, and we can even label this. I'll label this guy as an angle here, saying that's the start position. And what we'll do is we'll say it rotated counterclockwise to this position. It's less than 1 rotation. And then if you know the degree angle or the angle measurement, we would write that in. So 225 degrees. And that is how you would graph an angle or draw an angle in standard position. All right, an angle also, this is maybe a little bit beyond geometry here, an angle measurement could also be broken up. So, and the way an angle breaks up, there's 2 different ways. The first way, which we'll talk about here, is this part right here, which is the fact that an angle measurement could be broken up into pieces of 60. And so this is 1 degree over here, and that can be also broken up into 60, and we call them minutes. So we have something called degrees, and then if you break that up into 60 pieces, that would be minutes, and if you break minutes into 60 pieces, that would be seconds. So just like clock, and the question comes up is, Mr. H, how can we break it up by 60? What's up with that? It's because way back in history here, the Egyptians, the Babylonians, their number system was base 60. And so all their numbers were in terms of 60. And yes, they did a lot of astronomy And because of that, we just sort of kept that. It divides nicely. There's a lot of good calculations that come out of it pretty easily. And so we said, oh, let's just keep it. So there it is. Okay, so 1 degree broken up is the same thing as 60 minutes. And then, of course, if you take 1 minute, break that up, and that'll be 60 seconds with a double hash mark here. So that means if it's if we break up a degree into a whole bunch of seconds, that means 1 degree would be 3,600 seconds then, because it's 60 times 60. All right, with that, let's go for it. Practice problem number 2 says, can you convert this 13 degrees, 9 minutes, 22 seconds. Can you convert it into something called decimal degree notation? Now this is probably the one you're very familiar with, is the fact that you just have a decimal piece of a degree. That's all you have. All right, the most quickest way, there's about 3 different ways to do this, but the most quickest way is really just to go 13 plus, now the 9 is in terms of minutes, so we're going to go 9 divided by 60. Then we're going to take 22, divide that by how many seconds portion of a degree it is, which is 3,600. All right, plug that into a calculator real quickly here, and you should get something along the lines of 13.16. All we do is put a little degree symbol, and there it is. There's something called decimal degree notation. So it's the number of degrees and decimal pieces of another one here, rounded off to 2 decimal places. All right, sometimes we also want to go the other way. So instead of going from degrees, minutes, and seconds to decimal notation, let's go the other way here. 41 degrees, or 41.275 degrees. So what we do here is let's change this back to degrees, minutes, and seconds. Now this one just takes a little bit more effort, and again, also what we're going to do is we're going to round this to the nearest second. All right, let's go for it here. So take 41 degrees, and what we're going to do is we're going to separate it from whatever is the decimal piece here, 0.275. We're going to separate that out because that's really not a full degree. All right, think about how you would do this in terms of an hour. Let's say like this. Let's say 2 hours. If we multiply this by 60, we get 120 minutes. But notice real quick here, by just multiplying by that 60, what we've done is we've really changed the unit value on our time. That's exactly what we want to do here. I'm going to take this, multiply this by 60. Once we do that, now we're going to be in terms of minutes, or whole minutes. So the 41 degrees is still here, but now we get ourselves 16.5 minutes. So again, exactly what we're going to do here. We're going to separate the 16 from the 0.5. So 41 degrees plus 16 minutes plus 0.5 of something. And that something is going to be a multiplication by 60. Of course, once you do that, you're going to multiply that here. So we have 41 degrees, 16 minutes plus 30 seconds. Now this one's nice because when we did this here, it actually did round off to the nearest second here. If it doesn't, let's say as you multiply the something times 60, it turned out to be like maybe like 30.2. And if that's the case, then we would just still keep it as 30 seconds. If it was like a 30.7, then what we do is we just round it off to the nearest second, which then would just be 31 seconds. That's all. All right, final answer. We'll keep them all together, get rid of the plus signs here. It's going to be 41 degrees, 16 minutes, 30 seconds. So we have converted a decimal notation for degrees into degrees, minutes, seconds. Okay, one little trivia little thing here is the military, because they need to be extra little precise, they do have degrees, they do have minutes, they do have seconds, and what they have something called mils, M-I-L, or mil, and that also is another little precision point that they have, because when you launch a rocket halfway around the world, you kind of want it to land exactly where you planned it to land. and so they have to be extra precise. That's why they have an extra system of measurement. All right, so let's change gears for a second here. So we talked about degree measurements, and degree measurements fall into two different categories. So decimal notation, then you got degree, minute, second notation. But there's also another way to measure the distance in a sense of an angle. And here's the weird part. This is from your textbook here. The figure is sort of illustrated pretty well. It's something called radian measurement. And radian measurement really, in a sense, is talking about how many radii you have, or how many of the radius fit around that circle. So think about radian. In your mind, you should be thinking, oh, this has to do with a radius. All right, and as we do this, we take the radius right here. So we take from the central angle out here, we measure this part right here. So we say, okay, that guy is going to be R. That's how many unit values they are. And then what happens is we take that radius and we measure it out, and then we measure the outside of the circle that it makes. Remember, the bigger the circle, the bigger the R value is going to be. So kind of funny, no matter how big the circle is going to be, it's always going to be that same measurement. So what you do is you end up taking these R values, or the length of the radius, and you keep on putting it outside of that circle, on the outside. And so you go once, you go twice, you go 3 times, you go 4 times. You want to see, okay, how long is this going to go around the unit circle with? And it turns out to be 6, just a little bit more, 6.28. Like, huh, okay, that's not a number that I know from math. The funny thing is when you do this, if you were to cut it like this, if you were to cut exactly half of a circle. So now instead of measuring the whole entire circle, we measure 1, 2, 3, and this little gap right here. If you do that, half a circle is going to measure, well, let's see, what's 6.28 divided by 2? 2 goes into 6 3 times. 2 goes into 2 once, and 2, hey, anybody seen that number before? All right, and again, it's approximately 6.28, so that means approximately, if you go halfway around the circle, it's going to be approximately 3.14, but we know what that number is. Approximation to 3.14 technically is the exact value for pi, and that's exactly what it is. Half a circle gives you pi radians, or 3.14 pieces of the radius. To cover that. All right, so if that is the case, then really we have this. We have this little situation here. How do you convert between degrees and radians? And this whole thing comes up, is this whole concept is this, is that pi radians is equal to 180 degrees. I got that little degree symbol right there. So then we do this here. If we convert from degrees to radians, if we're converting from degrees to radians, what we do is we take a multiplier, and we multiply by pi over 180. I should do it like this. If we're trying to get from radians, we're trying to get back to degrees, what we do is we multiply by 180 over pi. And we'll see that in the preceding examples in just a bit. All right, let's just see a few examples here before we go on here. So if you take 30 degrees and you're trying to convert this into radian measurement, what we do is we take 30 degrees, we multiply it times the equivalent of 1 radian, which is pi divided by 180. And notice what happens here. The degrees are going to go away, because one's on top, one's on the bottom. And then really what you do is you simplify. And you got pi over 6. I have 90 degrees. 90 degrees, you're going to multiply that times pi over 180 degrees. The degrees cancel. And 180 goes into, or 90 goes into 180 twice. So we got pi over 2. Now, whenever you see a degree symbol, what that really means is you are in degree measurement. Normally what we do is we don't put radians all the time. Radians, radians. What we do is we just put it as pi over 2. If you don't see a degree symbol anywhere over here after the number, that means you are in radians. It's almost like the default value. And we use radians a lot. Let's look at 2 more examples here. What happens if the angle is negative? Well, that negative sign just sort of carry on through here. So negative 225, the degree symbol goes away, cancels. We'll reduce this as much as we can, and eventually we wind up with a negative in front still, so negative 5 pi over 4. All right, what happens on the homework when that number really does not reduce nicely with the 180? So 55 degrees, the degree symbol goes away. 55 into 180, that's not going to be very nice. It's going to be something we don't like. And I'll show you which ones we like and we don't like later on. So what's going to happen here is you just take your calculator and just put 55 times pi divided by 180. Now this homework is going to be a little different from these. The instruction for the homework like this is just going to say approximate the number of radians to 2 decimal places. So in this point you just put 0.96, and that would be pretty much it for that problem. All right, so your turn. Go ahead, practice problem number 3. Can you convert negative 45 degrees to radian measurement? Give you a little bit of time, and then we'll look at it together. All right, so negative 45 degrees. I'm going to multiply that times pi on top and 180 degrees on the bottom, even though I wrote it backwards there. That's okay. As long as the pi is on top, 180 degrees on the bottom. And here's what I want you to notice is this whole concept is the degrees go away. The degrees get canceled because one's on top, one's on the bottom. You are left with no more degrees. So because of that, you technically are in radian measurement now. Okay, so let's see what number goes into 45 and 180. I'm thinking to myself, 9 can do it. That's fine. You can also do it by 5. It doesn't matter which way you do it. I'm going to do it by 9. 9 goes into 45, or negative 45, negative 5 times. 9 goes into 180, 20 times. And if I forgot that 5 goes into 20, okay too, because when you go over here, you have still a chance to reduce it down some more. So then I can reduce these guys by 5. Got a negative 1 on top, 4 on the bottom, and eventually how about a negative pi over 4. And again, notice I'm not going to put the radians, R-A-D-I-A-N-S, at the end. I'm going to leave it as just negative pi over 4. There's no degree symbol here, so then automatically I know that this is in radian measurement. All right, let's go the other way now. So converting from radians to degrees here, what do? We take pi over 3. We multiply it now times 180 degrees divided by pi. And so the cool thing is, if your radian measurement has pi in it already, the pi's just get canceled, and really what you're doing is you're just taking that bottom value, dividing it into 180, which gives you 60 degrees. All right, negative measurement, still same thing. Don't forget to keep your negative sign there. So negative there, 3 pi over 4 multiplied by 180 degrees, degree symbol, pi in the bottom, and the pi's get canceled. So at this point here, I don't know, what do you want to do here? 4 goes into 180 first, if you like, or just use a calculator and do it that way here. And eventually, you're going to get yourself a value. Let's see, 4 goes into 180. I think it's going to be 45 times, and 45 times a negative 3 would give you a negative 135 degrees. All right, another piece of the homework is going to say approximate the number of radians. And this is cool too, because now you get to know what is the value of 1 radian. 1 radian, if you were just to take 1 radian and multiply times 180 degrees over pi. Now notice the pi can't reduce because there's no pi with that 1 over here. So again, on the section of the homework, it's just going to say approximate the number of degrees. or to the nearest tenth, I think. Okay, to that here, 180 degrees divided by pi, and it turns out to be 1 radian is about 57.3 degrees. 57.3 degrees for that. All right, so our turn. Here it is. All yours. Go for it. Can you convert 3 pi over 2 radians to degrees? All right, let me start as well. If you haven't done already, you're waiting for me here. So it's going to be 3 pi over 2. Again, multiplying by 180 degrees over pi. In this case, the pi's get to be canceled. That's the good thing here. So pi's are gone. And then also we can reduce this 2 in the 180 as well. So 2 goes into 180. About 90 times. So we're good there. And since we're just left with nothing but ones in the bottom, 3 times 90 gets you 270. Don't forget the little degree symbol. You got to put that degree symbol in there. So 270 degrees. And again, if you don't put the degree symbol in there, then it's going to be 270 radians by default. So that's not the correct answer. Cool. So, all right, 270 degrees. Another thing that comes from geometry is this whole concept of complementary angles and supplementary angles, which I think this would be review for you guys here. So just a quick review here. Complementary angles really are the angles that add up to give you 90 degrees. Supplementary angles are 2 angles that add up to give you 180 degrees. I think that's a quick review here. Practice problem number 5. So practice problem number 5 just says, can you find the complement and the supplement of 67 degrees? In this case, that's the easy part here. Remember, complement is 2 angles that add up to 90, but in order to figure out the complement of 67, all we really got to do is subtract from 90. So 90 subtract 76 degrees. If we do that, it should turn out to be 23 degrees. All right, the supplement is going to be what adds to give you 180. So 180 degrees subtract 67, and that's going to give you 113 degrees. All right, with this radian measurement here, what we do is we actually get 2 different formulas about a few things here, which really helps us in determining a few things in engineering. And so the first formula is something called the arc length formula. So the formula tells you how much is this whole piece right here. What's the length from here all the way to here? Okay, and the formula is S equals R times theta. A few little things here to note. R is the radius. Theta has to be in terms of radian. It doesn't work if it's in terms of degrees. Theta is in radian measurement, or in radians. Before we get to the practice problem here, I just want to show you where this good application is. If you think of terms of building a freeway, freeways don't generally turn right at 90 degrees, right? They tend to kind of go curve like this. Let's say a very tight curve right here. And so seeing this out is when you go into surveying or when you go into civil engineering here, what the general will do is they'll block off a segment of the road and they'll make sure that this length here is the same as this length, and they'll measure the angle here. Let's say that's theta. And so when they do that, they'll look at the arc length from here to here and they'll say, oh wow, that's 2,857 feet. And then what they'll do is they'll have to measure this wide angle here. Now, because the wide angle is going to be a lot further away. Here's the vertex in the sense of this angle here, because it has to be the same measurement here as here. Okay, and then they measure this angle and say, oh wow, that's more than 90 degrees here. That's a big angle here. And so I'll call it alpha. And so then they'll measure this piece right here and they'll say, oh man, that's like a 1.5 miles over here. And so because they're measuring the arc, they technically are just measuring the arc length right here, right? They're measuring that right here. And once they know that, then they know how wide the freeway is. Then at that point, they know the depth of it. Now they can order the asphalt that needs to be measured to repave the road or something, which I thought that's Kind of cool little thing I saw one time engineers do. Calculating the length of the road along a curve. Alright, so let's use our arc length formula here. S is equal to R times theta. And again, R is the radius of that circle. And the theta is in terms of radian measurement. So now we have ourselves a little problem. And the fact that the central angle is in terms of degree measurement instead of angle measure. So 225 degrees. I have to figure what we can do about that. And I'm thinking you know how to do this here. So I'll let you guys try this here. 225 degrees multiplied by pi over 180. So I'll give you guys a quick moment here to finish that off. All right, and again the degrees go away. And let's see, 225 and 180. Let's go by 5. 5 goes into 225 45 times. 5 goes into 180 36 times. Did that, and can I go down some more? Well, what does 45 and 36 have in common? Oh, 9, that's right. So 9 goes into 45 5 times. 9 goes into 36 4 times. And I got myself, simplify if I can make it here. So how about 5 pi over 4 as the conversion from 225 degrees to 5 pi over 4 radians. All right, so we are ready to plug it in. Plug it into the formula here. S equals, and the radius is 2 inches. Got that. And our theta is 5 pi over 4. In that case, let's see, the 4 and the 2 will reduce. That's good. So 4 and 2, 2 on the bottom, 1 on top. That's cool too. Now I got myself 5 pi over 2. And at this point, you probably want to do approximation for these, particularly for the arc lengths here. So it's approximately, so it's not a straight equal sign. It's kind of like a little squiggly equal sign. And that, and using a calculator here, finishing it up here, 5 times pi divided by 2, 7.85, and then of course don't forget the units that you are in. It says the radius, we had a radius of 2 inches, therefore we are in inches, therefore we have 7.85 inches. An application where this could be used at is to figure the distance on the surface of the Earth. Granted, the only thing that you really need to have is you need to have so that it's not sort of different meridian lines. So it's basically, in the sense, it's going straight up and it's going through pretty much the same meridian line. So we don't have the way to sort of go from, let's say, Los Angeles to New York, but if they're on the same line going down from the North Pole to the South Pole, or very close to it, we can figure out this right here. What we really need is, though, this whole concept of, we get angles of different cities based upon the central angle coming from the middle of the Earth, in a sense, along, in a sense, an XY, along the x-axis, so in a sense the equator. So we know those angles. So let's see how the example works out first. It says we want to figure out the distance from Billings, Montana to Grand Junction, Colorado. And so what we have is we have the latitude lines. So the latitude line of Billings is 45 degrees 48 minutes north. For Grand Junction, the latitude line is 39 degrees 7 minutes north. And what we use 3,960 miles as the radius of the Earth. So we got ourselves a little problem, because we don't want to know those particular angle measurements. What we want to know is we want to know the distance or the angle, the difference of the angle measurements between the two. So what we've got is we've got this angle measurement given, then we have this angle measurement given. But what we really want is we want the angle measurement in between those. So what we do, of course, is just subtract. So 45 degrees 48 minutes, subtract 39 degrees 7 minutes gives us a difference of 6 degrees and 41 minutes. At that point, now we're going to convert the degrees into radian measurement, and that gives us a angle measurement in radians. And then notice this little arc length formula. That's all we're trying to find. So we're trying to use the surface of the Earth, really in a sense, is the outside of the circle here. And so we have the radius of the Earth times the angle measurement between them. So that gives us 463 miles. Our problem. Here it is. So can you find the distance on the surface of the Earth from Chicago, Illinois to Pensacola, Florida? Cool. Let's see, my wife's two brothers live here, and my wife's best friend lives here. So that's kind of cool. Visited, have been here. Kind of cool place. Awesome beach, I gotta say. Have never been here yet, so we'll see. So to find the distance between Chicago, here's your latitude line or latitude angle, Pensacola. And we're going to still use this. And again, if you are ready, go for it. You can go ahead of me. If not, just wait up and we'll do it together. So first, drawing the Earth in a sense. There's my central point. There's my line going out to Pensacola. There's my line going out to Chicago. And then there's my line going out to the equator. There it is. So from that, we know this angle here is 30 degrees 25 minutes. Then we also know that this bigger angle here all the way to Chicago is 41 degrees 41 minutes. So now the question is, what is the angle in between? All right, so yes, we have to subtract. So big subtract small here. So 41 degrees 51 minutes, subtract 30 degrees 25 minutes. Let's see, got to borrow, of course, here. So how about 11 minus 5 is a 6. 4 minus 2 is a 2. Again, 1 minus 0 is a 1, and 4 minus 3 is a 1. So 11 degrees 26 minutes puts us right there. So that is the angle between Pensacola and Chicago. Or, as they like to say, Chicago. Chicago. Whatever. Okay, let's go. So, let's convert this into radian measurement here. Ooh, this is fun. I don't think we've ever done this before here. So how about 11 degrees plus 26 over 60, right? Because that will give us a decimal approximation. And again, we have to use approximations here. If we do that, punch it in a calculator here, you'll wind up that it's approximately 11.433 degrees. So converting 11 degrees 26 minutes to an approximate degree value, 11.433. Let's go on now, convert this into radian measurement here. So 11.433 degrees times pi over 180 degrees. And again, those degree symbols will go away. And of course, you're going to have to use a calculator here. So punch in 11.433 times pi, and then divide that by 180. And I got 0.1995. Hopefully that's what you guys got. And now we are ready to plug into our formula. Our formula, S is equal to R times theta. And so our radius, this is going to be the radius of the Earth, 3,960. And then the radian measurement from above that we calculated. So 0.1995, and we're good to go. How about multiplying that out? And of course, it's approximately 790, and we call it in terms of miles. So I can just put MI. If you want to put MILES, that's fine too. But the abbreviation for miles, so it doesn't get mixed in with the metric system, is just put MI with a little dot at the end. Okay, so 790 miles. That is the surface of the Earth calculation here, but I went to MapQuest and I wanted to know the actual distance from Pensacola to Chicago. So if you look on MapQuest, interestingly enough, you find out that it's a little bit different here. So you take the route, of course, you're making these angles here, and you make a little wide angle here, but you're only really traveling by car 913 miles. So I think that's quite a bit of difference there between 790, but 130-mile difference by going straight. The other angle that we have to deal with here is something called the area of the sector. So the arc length has to deal with the outside of the circle like this. The area now has to do with all of this here. So it's area. Area as you expand or widen out an angle. What do you get here? So this is our formula. So angle is equal to 1/2 times the radius squared times theta. As an example, here's a little example from the textbook here. So it says how many square inches of a pizza if you eat a section of an 18-inch diameter pizza whose edges form 30-degree angle. So don't forget this is a diameter, right? So then you got a radius here. It's going to be a little different. And then of course you have to convert the 30 degrees to radian measurement. As you do that, just real quickly here, 30 degrees becomes pi over 6. Plug it into the formula. Your radius is 9. Plug in the theta, and you have eaten approximately 21 square inches of that pizza. Our problem here begins with, can you find the area of a sector of a circle that has a radius of 10 inches formed by an angle of 60 degrees? So I have that to deal with here, very similar to the example problem if you want to just follow along, if you have the textbook in front of you here. But here is our formula. I have to plug into this formula here, and the first thing we notice, we've got to change that 60 degrees into a radian measurement. All right, let's take 60 degrees. Of course, going to multiply by pi over 180 degrees. And as you do that, again, degrees go away. So how about 60 goes into 183 times? That's easy enough. In fact, you can even take off the zeros real quick here. Whenever you have an angle measurement that has a 0 in it, or multiples of 10, of course, the zeros go away. So 6 into 18, 3 times. That's cool. And we get ourselves pi over 3. Alright, and I think now we're ready to plug everything in. So let's go for it here. So 1/2 stays as a half. The radius is 10 inches. That's cool. So we got 10. We're going to square that, and we're going to multiply by pi over 3. And as you multiply all that out, again, you can take a calculator, do that. That's fine as well. You can do a little bit of work just to simplify it out if you like as well. That's what I did. I went 1/2 times, let's see, looks like 100, looks like pi over 3. Put a 1 over the 100 here, and how about 2 goes into 150 times. Alright, so if they're asking for exact value, it says, what is the exact value? It's going to be 50 pi over 3 inches squared. Alright, if they're asking for an approximation to the nearest tenth or to the nearest hundredth, in this case it's 2 decimal places, so again, punch it into calculator here, 52.36. And again, we're going to put inches squared, because remember, area is always in terms of square inches. Alright, and the last kind of formula that we're going to be using here is something called speed. As we look at motion, how fast can we go? Talk about linear speed and angular speed. We're going to sort of put it together. That's what we want to do. We want to know how fast is an object traveling around a central angle. That's what we want to do. If you go back to now this whole concept of velocity, how do things go? How do we measure something going, or speed? If you think of linear speed, isn't like S is more like how long you go, the length that you go, divided by the time, right? So length that you've accomplished divided by time. That's called linear speed. Then we have something called angular speed. Angular speed is more of having to do with how many rotations are you doing, how fast is it something is rotating, particularly how much is the angle rotating. And so this really doesn't give you a sort of clear-cut way to do this. We're gonna sort of stuff these two formulas together. What we're gonna do is we're gonna make this formula here. We're gonna make velocity, how fast thing is moving, in terms of an angle. Okay, so r times, this is called omega, or lowercase omega in the Greek alphabet. So the book doesn't really make it very quite clear how this all works. So let me show it to you on the next slide. And so if we have velocity, velocity is how fast, how much you have gone divided by the time that you've gone, right? So if you've gone 100 miles and it took you 2 hours to do it, right? So then at that point you got yourself, you're at 50 miles per hour, right? So the miles are on top, the hours are on the bottom. Well, the same thing happens here. Velocity, and this is actually velocity, this is v. All right, so now let's change that into something that you're driving in a car, something that changes with an angle. So here's what we do. We say to ourselves, well, if you think back to arc length, remember the arc length formula is S is equal to R times theta. That's really what we're doing, is we're saying how much are you going around, right here, around a circle in a certain amount of time. So we have arc length divided by time. So again, if this took you, let's say this was 20 meters, and it took you 10 minutes to do it in, right? Then you got yourself a velocity. We're good? Okay, but what we do here is everything in terms of a radius, but we do have a formula for S. S is really R times theta, and then we have this little t on the bottom. And so what we do here is we take this r to the outside, we say, you know what, it's going to be this right here, and we give this a special little Greek letter for that. So it's going to be radius times omega. Omega has this little to it in the middle here. Okay, and what is this? This is something called angular speed. If you know how fast something is rotating, you multiply it times the radius, or how much is it away from the central angle, and you got yourself how fast is it going. An example from the textbook here. So let's say you have a 12-foot wire and you have an airplane that is making 12 revolutions per minute. So let's find the angular speed first, and when we know what that is, we'll plug in our radius and we will be done. Alright, so how do you convert to angular speed here? Well, we just multiply it by 2 pi. Why do we multiply by 2 pi? Because 2 pi is the circumference around a circle. So if it's 15 revolutions per minute, we say 15 times 2 pi. We want to know how fast is the angle changing. And so it's 30 pi. That's how fast the angle is changing. 30 pi radians per minute. Once that is set, velocity is equal to radius, which is 12. How fast the angle has changed in a single minute. And we got ourselves approximately 1,131 feet per minute, which is kind of cool. Practice problem number 9, which is the last problem here for this section. Find the angular speed and the linear speed of the plane in exercise 9, assuming that the wire now is 10 feet long. And now the airplane is going a little faster. It's making 18 revolutions per minute. So let's go for it. So 18 revolutions, again multiplying by 2 pi, would give us an angular speed of 36 pi, and again radians per minute. All right, what do we know about this? We know omega is equal to 36 pi. Once that is set, then we plug into our formula here. So velocity is equal to radius times omega. And so we have a radius of 10 feet times 36 pi. And we get a result of 360 pi, and this is in terms of feet per minute. Approximately, it's 1,131.97 or 1,131 feet per minute. The thing is, that's exactly the same answer as for the practice problem, and the reason for it is because we were going a little faster. We were going 18 revolutions per minute as opposed to 15 revolutions per minute. But then if you go back to the example here, but then in the example, the wire's 12 feet, and for our practice problem, the wire is only 10 feet. So you made something a little bigger, you made something a little smaller, ended up really being the same. So as far as the problem is concerned, that is perfect right there for the problem. But I want to go just a little bit further if we can. I know this is at 1,131 feet per minute. What I want to do is just go a little further than the homework or than the example problem really wants to. I want to go look in terms of this in terms of miles per hour. How fast is 1,131 feet per minute in terms of miles per hour? So let's go for it. And so we look at it, we're going to do something called dimensional analysis, something from chemistry class. Maybe you've seen this before. We're going to set up so our unit values give us exactly what we want. So we make these little breaks. So we start off with 1,131 feet per minute, and eventually we want to end up on the right hand side is miles per hour. So we make a little break here. We say to ourselves, okay, we got to get rid of feet. We want to go in terms of miles. So we know that 1 mile is 5,280 feet. And so we break that. So now I got exactly what I want. I got now in terms of miles per minute. That's what I wanted. So I can take off the feet here. Notice the unit values here. That's miles per minute. So miles is what I want on top. Now I got to get rid of this guy. So instead of minutes, now we're talking about hours. So I go over here and say, okay, minute's going to go on top, and the equivalent of it is going to go on the bottom here. So these values always have to be the same. So 1 mile, 5,280 feet. That is the same. 60 minutes, 1 hour. That's the same value. But notice what's going to happen here are the minutes get to be canceled. So now what units am I in? I'm in miles per hour. So now let's multiply this here. Let's multiply the 1,131 times 1 times 60 divided by 5,280. 80. And when I do that, I get myself miles per hour, exactly how I wanted it. And the calculator, it's going to be approximately 12.85. Not bad for a little airplane going around. It's going to almost 13 miles an hour around that little post. All right, well, that concludes the lecture for 5.1.